So the first one was UV light.
So is the trial a bit hard?
Well, look, first thing you got to realise, guys, is that any HSC exam, right, has questions from band 1 to band 6. So band 6 questions are designed for the top 10% of people, which means that in most courses there'll only be one or two people who'll answer those fully. So they're going to be hard questions in it, right? Some of the questions are really easy, some are really hard. I think the spread across is a normal sort of physics test, but because of where we were at with Year 12, they requested, and I granted that, not to have sort of the option topic sitting in there. What they want to do is the option topic in class as a practice test, which we're going to do. So what you guys will do is you'll get, pardon?
We're not doing the option topic.
So when you do your trial, the option topic won't be in the trial. You'll get to do it as a separate just class practice test, right?
Yeah, I think that's pretty physics.
But in the trial, there's only one question on the option topic.
Yeah, it's 25 marks.
25 marks.
Yeah. So what I've done, and what you get, what they got, is they get the normal trial exam. Then they've got an extra section in it, and that section was made up of 20 extra multiple choice questions and 5 extra short response questions, marks. Okay.
So is that part of the test, not testing
Yeah.
the optional topic?
That's right.
Why
Yeah.
are we testing option topics though?
Why aren't you?
Yeah. Why
Well,
do we-
because I want to give you the same exam as they got,
Yeah, I know that. but
obviously,
why do they get the-
and they got, because we're only through 1.5 main ideas, main ideas in the topic. We hadn't completed the course yet, and they didn't want to just be tested heavily on those little sections. It's fair enough, but they want to go doing the actual option topic test, so we just did it that way. Okay, UV, it's just part of the electromagnetic spectrum. And if you want to specify, which you should, it's between UV and what? Between visible light, DL, and which one's next?
X-ray, sorry.
Yep. That's all you need. Okay. Wish I could get some red in there, and I can if I do that. Try and keep it there though, that's the trick. All right, next one was it electroscope? Gold leaf electroscope, GL.
The text static charges by the position of a sheet of thin gold, like if it does this.
Yep, that's right. So it's a device for measuring static charge.
So that's what I had, but I don't know describe that.
I swear we've learned that.
Yeah, you were showing some do it that
I have used it.
Well, maybe that was part of one of my experiments.
No, you guys used it back in year 11.
No. Oh, yeah.
It's part of your prelim course. The next one was electric field.
So,
Electric.
so I wrote a device that can be charged negatively, which the electrons in the gold leaf will help.
Yeah, well, you can charge it positively too. The electric field in the region of space in which a charge experiences a force. Yep, I'm not going to write that out because you should know it. Then I put down wave formula.
W equals F lambda.
Now you could do wave formula is good enough to do this, which is W V equals F lambda. Or you could write an equation which describes the relationship between velocity, frequency, and wavelength in a wave. A region in space in which a charge experiences a force. A. Where a charge experiences a force. Just out of curiosity, I was talking to my son David, who's doing his second year courses in engineering, including electrical engineering, and they had to define power. in their lecture about this. And what do you think they defined power as?
Voltage times current.
Exactly. And I said, okay, what did the lecturer say that means? Because you can understand energy in terms of being able to do work and apply forces. And you can understand voltage, you can understand current. Current. How did he explain what this stuff called power is? And he said he didn't. He just said it was VI and left it at that. So even second year uni is just left at that understanding of it. Right, last one was classical physics.
What's the actual?
Physics pre-1900s.
Yes.
Yeah, boys.
Or you could put, that's definitely a good one, physics
Does that mean suit out physics pretty much?
explanations. It's pre-1900s. Or you could put, and don't forget, it's not, classical physics guys are not rubbish physics. We still use it and use it very successfully for lots of things. Perhaps another way of putting it is pre-Einsteinian physics.
That's okay to do in a practice.
Now, a couple of things quickly for you and full attention on this. First up, this afternoon after lunch is when I was going to put one period aside for doing the prac. If you're not ready to do it today, I'm happy for people to do it tomorrow. And what I said we'd do last week, to make it clear, is I would set some work that people can do independently this afternoon while other people are doing experiments. So you can do the photoelectric work this afternoon and do your experiment tomorrow, or you can do your experiment today and do the photoelectric effect stuff tomorrow, but it will be independent. Yep.
We came in at lunchtime, say like half time. Could we get going and setting up and stuff like that?
Yeah, that's fine. I'll just open up the lab and leave you to it. That's not a problem. The other thing you guys have to realise is that we will finish photoelectric today and tomorrow. Thursday afternoon, unfortunately, Friday and Monday, I have to go. I won't be in. Now, that wasn't planned. It's just happened that way. And you guys need to keep working, obviously, at that stage. So what I'm going to do is going to set up on Moodle, finish setting up on Moodle, the last main idea, and it will have all the work you need to do that main idea. So on the Thursday afternoon, Friday, Monday, I'd expect you on your own to basically be able to knock over 90% of that. Okay? So I'll be self-gotten. Yeah, there'll be someone in the classroom with you, but you should be able to work your way through the majority of that and understand it. Yeah.
Because if we're not doing the practice now, can we do looking at option topic now?
I'm going to do that. I'm going to work my way through a number of things. Third thing, most of you got notification of the online task on Moodle, and I asked people to make sure that over the weekend they checked it and made sure they could actually log in.
So
Yeah.
I keep getting kicked out of the physics course.
Do you?
Yeah.
That's unfortunate. Okay. Let me show you. Right. If you can't find it, you go to Google, you type in Moodle, Corowa High, login. Click on that. Do the authentication I have to do. Right. This machine is getting over authenticated.
You know, Stan. No, actually, like, having your own Mac and work with me, which is sort of like a slap in the face. So that's the same. Like, you know, Stan from my dad's office. It has you know, computer. It's like, you know how when you go online. Yeah, Stan. He has a whole gig of RAM.
Does it show conversion of electricity into motion? Right, so you go in here. Sorry about that, we'll concentrate what was asked. So you go in there, if you type Corowa this time, high school Moodle login, you do that. If you go to the very top link, and that will take you direct to it. Okay. Yes. Yes, Brad. Sorry.
Yeah, so first question is, you know how it doesn't work when you're not there on Thursday?
And Friday and Monday, yeah.
Yeah. So you're just going to leave like the dot points that we're supposed to achieve, and like, you know how some of us have that physics and focus tool?
Yes, you can work through that, but what I'll do is on Moodle, I'll actually say you're doing main idea 4 for ideas to implementation. There'll be all the dot points there, and I'll just ask you to work your way through the material on those dot points. Okay?
So
That's how you do it.
we're allowed to do that.
Yeah, the idea, because look guys, what all I'm asked to do is to give you, put it away, all I'm asked to do for you guys is to give you the opportunity to learn what the syllabus asks you to learn. Now I deliver you a whole lot of material and give you that choice, but I reckon you're old enough, mature enough to work out for yourselves. If you have an alternative method that suits you better, go for it. But what will happen is those days I'm away, Moodle will be set up, it is set up, so that all the material you need to cover those dot points is there. There'll be PowerPoints and videos and worksheets and that sort of stuff. If you want to go through those dot points using those things and learn it, that's great. If you prefer physics and focus and you work through it that way and you get those dot points done that way and you can succeed at all the questions and tests, that's great too. You just need to know what's in the syllabus, yeah.
If we don't go to Cool Heads tomorrow, what do we do? Do we still like rock up to regular class?
Yeah.
Yep.
Yep.
No, he would
Now,
care if I can go to Cool Heads.
next thing,
What do you even do at Cool Heads?
could do.
They're basically trying to scare you into not drink driving and not
What's the enrollment key for
Is there an enrollment key?
I can't get kicked out.
I think it's capital N Newton. Yeah, capital N Newton. Okay, cool heads. You guys go from being at the safest stage of driving career and your L plates to the most dangerous part of your driving career, which is red P plates. And what they're trying to do is show you the consequences of poor decision making when you're driving. That's essentially it.
What happens if you already know this?
You may think you know, but on the whole, teenagers are very bad at actually visualising and connecting with that stuff. Okay, last thing we need to do before we go crazy with our work today. We need to do our votes around our option topics. So, I know. I can only wait so long.
Yeah, can somebody message Cody? Can somebody just message him while ask him what
You have him on Facebook, Dad.
Yeah, no, doesn't he want his 2 top? Yeah, so what do you want to know from Cody? His top 3 is
On the class.
Yeah.
On the class.
It's like really sort of quick rundown.
Really briefly, medical physics is where you look at the application of physics to medicine, particularly in diagnostics, although there is some therapeutic. Diagnostics being determining what the medical issue is, and therapeutic is actually doing some treatment. You work around a number of techniques and look at how the physics applies. So you look at ultrasound, X-rays, CT scan, PET scan, and nuclear medicines and their application and MRI. In geophysics, again, you look at the application of physics to understanding the Earth and other planets. You start off by looking at what's the concept of remote sensing, and understand what remote sensing is, particularly the difference between active and passive remote sensing. And then you go and you look at various aspects of understanding the Earth's crust, building upon the stuff you did in year 9 and 10. So you look at geomagnetism, and you look at how rocks, now you don't look specifically at rocks, you don't have to know a lot about geology, but you look at how magnetism is stored in rocks and how there are patterns of magnetism, how that gives proof about tectonic processes and plate spreading. You look at gravity, and you look at how the gravitational methods were discovered, and you look at how they are used today, and how they're detected and what causes them, how they're used to look for oil and gas, and how they are used to support tectonic ideas. And then you go and you look at seismic events, learn a little bit how we record earthquakes, what those recordings mean, and show us what the instruments are that do it. And you do one crack, which is extremely hard to get hold of, but I've managed it, where you have to use seismic waves to work out the depth of a layer of the Earth. Then you have astrophysics. Astrophysics is a course. Astrophysics is a course which essentially maps out a couple of things. It maps out how do we understand about space and about the objects in space. And of course, our primary way of doing that is looking at the spectrum, particularly light. And so we look at the idea of the luminosity of stars, and we look at the idea of apparent and absolute magnitudes and what they tell us and how we work out distances to stars and things like that. We then look more carefully at the life cycles of stars and the different types of stars they are. And then to look at things like distances in space and so on, we have to look very closely at pulsars and quasars and things like that, and look at how they operate. Yeah, Tom.
Which has the most mass in it?
Astro has one extra formula. Geophysics has a formula. Medical has 2 formulas. Astro has a couple. Quantum of quarks has a couple. Age of Silicon, you need to understand NAND and that stuff, logic. So Age of Silicon is actually looking at how chips work in computers and how logic gates and those things are made, understand the mechanics of how the signals are sent around logical systems and the sort of architecture, the physical architecture, the why physics determines that. And quantum to quarks, in really brief form, is really just looking at an intro to quantum mechanics and look at people like Pauli and the Pauli exclusion principle and the uncertainty principles and all those sort of things that go on in it.
Anything like the development of the atom, whatever?
Yeah, you look at the history of the development of Niels Bohr theory of the atom and that sort of stuff, but it's basically an intro into quantum mechanics. Okay. Medical.
Does it matter in next month?
You don't do the same thing, no? So,
Wants to know about implants.
shh.
I know.
Okay, while we're waiting for others, what we'll do is we'll get on and we'll do this.
We're all voting, so.
Yeah, let's count the votes. Let's make the votes. It's interesting.
Okay, in the Moodle, there's in fact a PowerPoint there, which is made by another teacher, which summarises all of the ideas to implementation course.
Really?
All of it. Yep. Now, what you'll see here is it talks about Hertz and his work, and it actually talks about the fact that, as we talked about Hertz places the receiver in a darkened box to make it easy to see the spark. But he noticed that when he did it in this particular type of box, the sparks he was looking for were not as distinct. And it says, after much tinkering, Hertz discovered the sparks jumped the gap in the receiver greater if ultraviolet light from the initial spark was shone into the gap. Although this was the most amazing discovery, Hertz did not further investigate this phenomena, but went on to look at EM waves. And as I said, he had noted that, and he actually wanted to look at it, but didn't get to it. Now, what it wasn't left there, but as it says, J.J. Thomson did some experimentation on this, and he noted that it was electrons were being emitted. He identified, don't forget, that there was a particle. He called it a particle that was called he named the electron after much debating with himself, and he determined that the sparks given off as a result of the UV light shining on something were these electrons. So they're doing something to the electrons. There's some pictures of Hertz's experiment.
Is that sort of kind of like a transformer in a way?
Robots in disguise.
That bit there, the induction coil is the transformer.
So since we've got all the votes in, can we do it now?
Look, I want to quickly go through this. I'll give you something. I'll tell you what, if you're all keen about the votes, rather than me finishing this off, what I'll do, yeah, that shows a lack of discipline, not a fault with my methods. So what I'll do is,
You work at how, you look at how MRIs and stuff like that work.
all right, let's move on to what we have to do now. So, no, it doesn't need any further discussion. And let's face it, someone was always going to be disappointed at the end of it, so that's just how it goes. Okay, so we talked about black body radiation, and they begin to talk about the order in which you see light given off as you heat objects. So you get the red first, through yellow, finally white. And what they found, of course, is that the dominant wavelength of an object is directly related to the temperature of the object. So there's some sort of relationship between heat, temperature of an object, and the colour it is, which is really useful in astronomy. Sorry for those guys not going to astro, but it does show that you can work out the temperature of a distant object by looking at the temperature, by the colour of light it gives off. And when this loads up, to completely understand how the wavelength of radiation varies with temperature, there are experiments carried out with these things called black bodies. And we talked before about definition of black body, which is something you need to know. A perfect emitter and absorber of energy. And they talk about that process. And I'm just rushing through this background because you've already got it. So all light that enters a hole, and you have a black body with a cavity in it. It's called a cavity emitter. What you can do is you can channel radiation into that hole, so it heats the internal part of that black body, and then you can turn off that source, and then it will emit radiation out from that. But you end up with some variations on what the emission there. And there's a picture of a experiment showing a black body emitter. Okay.
I understand how that black body emitter actually works.
All right. So what you do is you just expose it to a source of radiation for a certain amount of time. It will absorb that radiation, then you turn it off, and then it will re-emit that.
So that could just be like a piece of charcoal.
It practically is. It's soot black is what they have used typically.
Right, same as if you say like got a black piece of charcoal and got something that emitted alpha particles, and you shone it on that like piece of charcoal for a long time, then took it away. That piece of charcoal would just
Then radiate out, not alpha particles. If it absorbed them, it would then radiate out probably electromagnetic radiation.
But like, what would it be? Would it be heat, or is there no?
Well, it depends how much energy it absorbed as to what it would emit.
So like if
The whatever it emits, the wavelength it emits at is related to how much energy it absorbed, which is shown up as what we call heat.
so like you could expose it to alpha particles and it would actually transform that energy into something else that would emit that.
They're emitting it's electromagnetic radiation in some form.
So you could make charcoal radioactive by shining something like radioactive.
If you bombard something with radioactive particles, you don't tend to make it radioactive, you tend to change it into other stuff. You tend to transmute it. Right, oh sorry. So what they do is when you do that, you can pull up the graph. We've seen these graphs, all right? And you see that how as the energy increases, the heat essentially increases, so you get a change in the wave pattern that goes with it. And that shows the temperature dependence, shows the temperature dependence of the waveform you get. The shape of the curves represented a problem for scientists trying to explain intensity and wavelength variations, because the classical theory, as we said, would predict that as the black body becomes hotter, the wavelength of the peak emitted would become shorter and intensity, or the amount of this peak would increase. So as the oven becomes hotter, it would produce more blue light than other wavelengths, etc., appear blue. Yeah,
How many votes did you get in before I told you codes?
all of them.
No, before I told you codes, how many votes did you get in?
What do you mean?
Like how many pieces of paper?
8.
Okay, just making sure.
So that wasn't a problem in some way, but the predicted curves didn't work for that. So you can see that there's the there's the curve that classical theory should produce, and there's the actual one, and that was produced a real question. And it's the UV side of this thing that presents us with the real problems. It came up with what we call the UV catastrophe, which we talked about.
I don't say what.
Okay.
How classical physics said that. I don't say what it actually saying.
Well, it essentially says that as you increase the amount of energy in something, that the wavelength should continue just to keep scaling up past UV into the X-ray and whatnot, but they don't see that, and they have to explain it.
Why didn't it?
Well, that's what we're going to explain to you. So,
Thanks for going the way you said you did. Thanks for voting.
that's right, I always try and make it democratic. Now,
Oh, no. If it was in the Astro the other way, then I think that calls for a recount in every other direction.
no. Now, the thing is that German Max Planck, and there's a picture of Max Planck, came up with his revolutionary idea, which he talked about, which was that we had the discrete quanta or packets of energy, right? And it led to a successful explanation about that particular curve. But he had no direct experimental evidence for his theory. Well, that's the claim here. I actually don't think he forgot about it. I believe it was actually talked about, published at times, because Albert Einstein actually used it to look at the idea of the photoelectric effect. Now, the photoelectric effect was another thing that classic,
What's the name of it? Is quantized.
right, in small bundles.
So light is quantized.
Yes.
And the
So,
quantity is.
you got this question about the photoelectric effect again. So we've seen black body radiation, no problem. Had the photoelectric effect. And in 1900, Philip Lenard showed that the photoelectric effect is actually the emission of electrons from the surface of material. And I have a track which is supposed to show that. So when you get electromagnetic radiation striking a metal surface, if it's the right sort of wave hitting it, you'll get the emission of electrons. Now here you've got light striking it, nothing is happening. So we know that it happens best in which part of the spectrum.
So photoelectrics is from off. That's
Oh, this in the blue range here, there are some going there.
right.
So if you get the right, you know that for red, red light, Hertz didn't see much of a response, did he? He didn't see any change. But for UV light, he did see an increased
How do you test
reaction. He just did it visibly. But this is the classic test here.
Essentially, like solar panels use black bodies to convert.
They actually use the photoelectric effect, not black bodies as such.
But
Yeah.
they use the photoelectric effect to convert.
Don't forget, black body's one thing, photoelectric's another.
Yeah.
Well,
Okay. Now,
So he got a red light and shine up.
no. When he had it in a when Hertz was doing his experiment, in the box, he could see the spark, but it wasn't as intense. And when he experimented, he found that UV light was the thing that gave him the best spark.
So he shined a.
No, he didn't have easy access to UV lights and things. So it's in sunlight that he filtered.
That's pretty much how solar panels work. They
Yep.
just comprise of all those little tiles everywhere.
Yep. What you see here is a picture of a classic experiment you're going to use. You notice that there's an ammeter, a variable power supply, and there's an emitter and a receiver. Now what's happening is light is shining on this piece of metal, and if it's not the right wavelength, you don't get any electrons fired across. If you shine enough light on it of the right frequency, electrons will go across to there and there will be a current shown on the ammeter.
Why is there a power supply there?
Right, about to say that. If the power supply is not in there, you just see a current there. But you can turn the power supply on in the reverse direction. Notice that's the negative side. So if that was turned on,
That's going to oppose
it's going to oppose it. And you can turn up your voltage slowly until you stop any electrons arriving at that plate. And I'll explain why in a moment, because the bell's just gone. That's an important part of the experiment.